This is Vodcast 9A. In this unit, we're going to talk about gases and liquids. 9A, we're going to talk about the characteristics or properties of gases. In B, we're going to get into the gas laws. And C, we're going to talk about the composition of gases and do some gas stoichiometry problems. Some things we need to introduce in this unit include the properties. We're going to compare gases, liquids, and solids. We're going to review intermolecular forces again. We're going to do a lab that involves the kinetic molecular theory of gases. Of course, if you're talking about gases, we have to talk about pressure. There's going to be several different gas laws that we're going to talk about, including Boyle's, Charles, Lusac, Avogadro. They're all going to deal with that PV-TNR stuff. P is pressure, V is volume, T is temperature, N is the number of moles, and R is the gas constant that we're going to get to. The ideal gas law is PV equals nRT. It's another one we're going to study. We're also going to talk about Dalton and his law of partial pressure, as well as the definitions of effusion and diffusion. And then, as I said before, in video C, we're going to do a couple gas stoichiometry problems. First, let's talk about gases. What are some properties of gases? They are fluid. What does that mean? They flow like liquids. If you pour them, if you could pour a gas, it would pour like a liquid. They are in constant motion. They do not stop. They're vibrating, rotating, translating. They have the lowest density compared to solids, liquids, and gases. You can see that from this picture. Here's an example of a solid, liquid, and gas. You can tell that these gas molecules are much further apart from each other than they would be in the liquid or the solid phase. And because they're further apart, they are mostly empty space. So we have some particles in this container. It has to be a closed container so it doesn't leak out into the room, right? You can see the gas particles, but what's in between the gas particles? It's nothingness. It's empty space. Other properties include the fact that it is highly compressible. If you had a balloon filled with some kind of gas, you could compress it. If you had a balloon filled with liquid or solid, they are not compressible. They are incompressible. Gases exert uniform pressure in all directions. When you're blowing up a balloon, it blows up in a uniform fashion. The particles that are colliding with each other and colliding with the container, they bounce off each other and they bounce off the surface, and that's what causes the pressure and allows the balloon to inflate. Kinetic molecular theory. This is what we're going to do our lab on. We assume ideal behavior. We assume that the gases follow all the laws that we're going to study in video B. We're also going to assume they are in not just constant motion, but they're in constant random motion. There's no set pattern to the way they bounce off each other and bounce off the walls. There's no attraction between the particles. Why? Because they're so far apart. It's mostly empty space. The collisions between the molecules are elastic. Elastic, think of a rubber band. If you stretch it, you pull it, it bounces right back. So if the particles are colliding with each other, they just bounce right off and move in a different direction. We're not losing any speed, velocity. We're not losing any kinetic energy when the particle hits something else, like the wall or another molecule. We're going to ignore the volume of the actual molecules because the volume is mostly empty space. And last thing it says, average kinetic energy is related to temperature. That means as you increase the temperature, there is a relationship to the kinetic energy, or to how fast a particle will move. If you increase the temperature, the particles are going to move faster. So when they both increase, when temperature goes up, speed, kinetic energy goes up, that's called a direct relationship. So, here's a question for you. If I have these three substances, I have a block of copper, I have some water, and I have some air in a balloon. If the average kinetic energy depends upon temperature, and I have all these three things sitting in this room, which one has the greatest average kinetic energy? If kinetic energy depends on temperature, which one has the greatest average kinetic energy? If they're all at room temperature, they're all about 70 degrees Fahrenheit. So if they're all 70 degrees Fahrenheit, nobody has the greatest average kinetic energy, because average kinetic energy is the temperature. So if they're all the same, why is one a solid, one a liquid, and one a gas? Well, we have to go back to the intermolecular forces, the forces that exist between the molecules. We studied this several units ago. There are weak intermolecular forces, such as the London forces, and there are strong intermolecular forces between ionic compounds. The stronger the force, the more likely it is going to be a solid. The weaker the force, the more likely it is going to be a gas. And then liquids fall around the middle. So the stronger the intermolecular force, the more likely it is going to be a solid. Gases have the weakest molecular forces. Why? Because they're so far apart, it's mostly empty space. They can't actually interact with each other as well as a solid could, because these guys are much closer together. They're more dense. There's more stuff packed in the same amount of space, so they're closer together, and the molecules can have intermolecular forces with each other. Pressure. When we talk about gas, we have to talk about pressure. Pressure is some kind of force exerted on an area. So what's this force caused by? There has to be particles or molecules out there for something to be a force. For solids and liquids, where do the forces come from? It's kind of obvious, isn't it? They're packed together. But what causes pressure in a balloon? The gas pressure in a balloon filled with a gas, is caused when the particles inside the balloon collide with the molecules and the surface of the container. So as they're bouncing about, they're actually causing the pressure that allows the balloon to inflate. There are several different units for pressure. One is the Pascal. It's the force over some kind of area. So the force is measured in newtons, and the area is measured in meters squared. Do we have to know Newton meters squared? We need to know these conversions. If you take a look inside your periodic table, or maybe on the back page, these conversions are given for you. You just need to know how to use them. So what is exactly a Pascal? Well, here it says 1 Pascal is equivalent to the force exerted by a stick of butter spread over an area of 1 meter by 1 meter. It's probably not very much. But what's the atmospheric pressure? You hear when the storms are coming in, the atmospheric pressure changes. It's high pressure, it's low pressure. If you have allergies or sinus time, you can tell when the pressure gets higher just because you can feel it in your head. The atmospheric pressure is the mass of the air over your head. And it can push down more or less. It can change depending on if it's cold or hot or what kind of front is coming in. So how are we going to use these conversions? We go back to our FLM. I'm going to skip a couple slides and then come back to it. We go back to our FLM. How are we going to convert these things? Well, I'll do this first one for you. What is 724 millimeters of mercury? Convert that into kilopascals. 724. Same thing as always. We start with what we're given. millimeters of mercury. I want to convert into kilopascals. Well, here's millimeters of mercury. That can get me to 1 atm. 1 atm stands for 1 atmosphere's worth of pressure. And then 1 atm is also equal to 101.3 kPa. So, if I wanted to simplify this, I can also say that these two are equal to each other because they both equal 1 atmosphere. So 760 millimeters of mercury has to go on the bottom, right? My units have to cancel, is equal to 101.3 kilopascals. If you punch that out on your calculator, you should get 96.5 kPas. Now, here's question number 2, 3, and 4. See if you can do those 3 conversions into torr. Here's your conversion for torr. That would be number 2. To ATMs would be number 3. And into PSI, which you may have heard of, PSI, pounds per square inch. It's how you inflate basketballs or tires, car tires, bike tires, PSI. So pause the video, see if you can do calculations 2, 3, and 4, and we'll check them. I'm going to go back a couple slides to where we left off, talking about pressure. Here we're going to talk about how pressure is measured. There was this guy, his name was Torricelli or Torricelli. He came up with this, here's a diagram for it, apparatus to measure pressure. Again, you may have heard of this in the weather, the atmospheric pressure. It's measured in mercury, and he's measuring it for every milliliter. He put mercury in a dish, and he had this big long tube that's marked with each millimeter. So what happens as the atmospheric pressure increases, the volume in this tube goes up. So if standard atmospheric pressure is right here, 760 millimeters of mercury, and the weather is such that it increases the atmospheric pressure, we're pushing down, which makes this go up further, the mercury is going to rise in this tube, and you'll be able to read it. If the pressure decreases, and it comes out, it's going to come down the tube into the dish, and your volume recording, kind of like a thermometer, would now be lowered. So when atmospheric pressure increases, you get a number higher than 760. When atmospheric pressure decreases, you get a number lower than 760. Here's the unit. Millimeters of mercury. He decided to be super clever and name those units after himself. So 1 millimeter of mercury is equal to 1 torr, or 760 millimeters of mercury equals 760 torr. That's the standard for 1 atm, 1 atmosphere of pressure. Now, why not use water? In the wintertime, water would freeze. We can't have much movement because this has to be outside, or it's usually outside, the barometric pressure. In the wintertime, it would freeze. In the summertime, the water would evaporate. So mercury is more stable because it's a liquid. At room temperature, it has a wider range before it would freeze or evaporate. So that's why he chose to use mercury. So here's our standard. Next unit, we're going to change our standard. So this one isn't valid right now. But in this unit for gases, you must remember this. The standard is 1 atmosphere and 0 degrees Celsius. If you recall the conversion, K equals C plus 273 for temperature, that's where we get this 273 Kelvin. So, standard, star this, highlight this. The standard for the gas unit is 1 atmosphere and 0 Celsius, or 273 Kelvin. STP, standard temperature, standard pressure. What do the symbols mean? P stands for pressure. Pressure is always measured in atmospheres. We just said that was the standard. V is the volume. Volume will always be measured in liters. N is the number of moles of the gas. T stands for temperature. We have to convert to Kelvin, so Celsius plus 273. And R we're going to get into later. It's called the universal gas constant. We'll bring that up next time when we need it. Effusion. Again, we're talking about gases. Effusion, here's your definition. The escape of a gas through a pinhole that doesn't have, without, any molecular collision. So in this diagram, I have 2 sections to my enclosed box. If all the gas is trapped in this right section, but you cut a hole in between the divider, eventually some of the gas will escape into the vacuum, the empty side of the box. Gases are going to move from high pressure to low pressure. Think of a can, if you use spray deodorant or spray perfume or anything like that. In that aerosol can, hairspray perhaps, it's a very, very high pressure. When you hit the little button, what happens? It escapes through this small, the hole in the little sprayer, to an area of lower pressure or whatever your surroundings are. There's an equation that you can use to calculate this, but we're not going to use this equation. That's an honors level thing. What we're going to say is that it has to do with the mass. In order to understand how this mass works, we're going to have another definition. Effusion is the escape through the hole. Diffusion is the mixing of the gas molecules out in the room. Random mixing, when the gas particles are now going to collide with one another, they're going to have collisions. So, here's gas 1 on the left. Gas 1 has a different mass. Let's say this mass is higher. And gas 2 has a lower mass. We're going to use that Graham's law from the previous slide to assume that something with a lower mass, let's think about this for a second, something with a lower mass is able to move faster than something with a heavier mass. We're still moving from higher pressure to lower pressure, and also higher concentration to lower concentration. If all the gas 1 particles are on the left side, that's highly concentrated of gas 1, it's going to have the natural tendency to mix with gas 2. We won't be doing any exact calculations, but we're just going to assume that the thing with the higher mass is going to move a little bit slower than something with lower mass. Think about the football players. If someone has much bigger mass, they might not be able to move as fast as someone who is light and runs track. So write down any questions you have on video A, and we'll talk about it when you come to class.